So I decided to concentrate on one theorem that indeed I was excited about since my beginning, even as a student. So the talk will be, I think, technically very accessible. What I would like to ask you is to wait for the motivation. The problem of motivating in such an interdisciplinary conference is difficult, but I hope I'll be able to transform to you some of my enthusiasm about this theorem and its extensions and problems related to it. So before I start with Tverberg's theorem, let me remind you of an even older theorem of Radon. And Radon's theorem says that whenever you have d plus 2 points in Rd, you can partition them into two parts so that the convex hull of these two parts have non-empty intersection. So here is the situation for the plane. Here we have 3 points and 1 point which lies in the convex hull, and in this case the partition will be, one part will be these 3 points, and the other part will be this single point. If the 4 points are in convex position, then you have to partition the points according to the diagonals. And then you have partition to 2, so the convex hull intersect. And Radon's theorem is actually a very simple theorem to prove, because when you have d plus 2 points in Rd, they are affinely dependent. And then you just write the affine dependency and move the points with negative coefficient to the other side, and then you see and then you divide by the sum of the coefficients, and you get a partition to 2, and you get a convex combination of one part which equal to a convex combination of the other part. Let me mention that if you look at, I forgot to say that when you have such a collection, when you have such a partition is called Radon partition, and the point which lies in the intersection of the convex hull is called the Radon point. And if we have collection of points, if you have collection of points on the line, then understanding the Radon partitions amounts to understand the ordering of these points on the line. So in some sense, this gives you a natural extension of the notion of ordering to higher dimension, which was studied. And when we have points in higher dimension Euclidean space, understanding the Radon partitions is called or two configurations with the same Radon partitions correspond to the same order type or same oriented metroid. And this is a very useful notion in combinatorial geometry. And indeed, there is axiomatization which give you more abstract objects which are not always representable. But now let me present you what is Tverberg's theorem. So Tverberg's theorem deals with a similar situation, except instead of dividing the points to 2 parts, you want to divide them to 3 or more parts. So if you have d plus 2 points in Rd, you can divide them to 2 parts where the convex hull intersect. If you have 2d plus 3, you can already divide them to 3 parts where the convex hull intersect. If you have 3d plus 4, you can divide them to 4 parts. And the formula is that if you have d plus 1 times r minus 1 plus 1 points in Rd, you can partition them into r parts, r disjoint part, so that the convex hulls of these parts have non-empty intersection. So here is an example of 7 points in the plane, and this is the partition to 3 parts. One part is the triangle, 2 other parts are the line segments, and there is a point in common. So Tverberg's theorem was proved by Tverberg in '66, and then Tverberg himself found a somewhat easier proof in '81. These two proofs were quite difficult. It was very difficult. Once I taught in class the second proof, and it took 6 hours, something like that. Then Tverberg and Verchika and Sarkaria found at the same year much simpler proofs. Actually, although a new proof is found every 6 or 7 years, I heard about these two proofs exactly the same day. And Raudnev recently found another a very nice simple proof. And since I want to invite you to this theorem, so let me first prove it to you. And here is now I will describe to you the proof by Sarkaria. So Sarkaria used the following theorem of Imre Barani. And here's the theorem. Suppose you have D plus 1 sets A1, A2, up to AD plus 1 in RD, and you have a point which belongs to the convex hull of each one of these sets. So this is the condition. And then the conclusion is you can choose one point out of each set so that X will belong to the convex hull of this D plus 1 chosen point. So you can choose A1, little a1 from the set big A1, little a2 from the set big A2, and so on, so that X will be already in the convex hull of this D plus 1 points. And note that if all the AIs are the same, this is no other than an old and classical theorem of Karateodori, which says that if a point in RD lies in the convex hull of a set, then it's already in the convex hull of D plus 1 points in the set. Okay, now this is a Barani theorem, and now in order to prove Barani theorem, we will just argue we will just try to find the minimal distance between such a convex hull of A1 up to AD plus 1 to a point, to X, and try to reach a contradiction if this minimal distance is greater than 0. So let's go on with the proof of Barani theorem. Suppose we have a point, so here, suppose we sorry? Yeah, so I'll put the previous one here.
Even the previous one before that.
So I'll put the previous one here, and the previous one before that, it's Tverberg theorem. Oh, okay. So now we would like to consider a point P, which is the closest point to a convex combination of this nature, x1 up to A1 up to AD plus 1. And of course, the hyperplane, which, I need also a picture, but I think I can squeeze here also the picture. Okay, so, well, this is X. And the hyperplane, which contain P and perpendicular to the line segment X from X to P, must support this convex hull, A1 up to AD plus 1. And therefore, P, this point P, must be in the convex hull of the points among the AIs which lie on this hyperplane. And therefore, by Karateodori theorem, it's already in the convex hull of D of the points. So we saved one point. So X is in the convex hull of D of the points, and let's say that, P is in the convex hull of D of N minus 1 of, what happened here? Oh, the indices are N should be D plus 1, I'm sorry. So P is in the convex hull of all the points except the J's point. So you see here, we could give up the point A3. So this means we have a chance to reduce the distance by replacing AJ by another point from the set AJ. But why can we do this? Because X belongs to the convex hull of all the points in AJ. This means it's impossible, look at this picture for me, it's impossible that, in this case, J is 3, it's impossible that X, this point X, if X belongs to the convex hull of all the points in big A3, it's impossible that all these points lie in this part of the hyperplane. Therefore, we have some point A3 bar, or AJ bar, in this case, which lie in this open half of this hyperplane, and now we can make a shortcut. So we look at the convex hull, the line segment which contain P and A3 bar. We have here a smaller distance, and this line segment belongs to the convex hull of all the points A1 up to AD plus 1 and AJ prime. So this should be D plus 1, and this is D plus 1. Okay, so this concludes the proof of Barani theorem. And now, is it clear? Now let me go on with the proof of... Okay. So let me go on with the conclusion of the proof of Sarkaria proof to Tverberg theorem. And now here comes the really nice idea. Now we have m points, and m is this number, d plus 1 times r minus 1 plus 1, in Rd. And it will be useful to look at them as points in Rd plus 1 whose sum of coordinates is 1. So this is useful for the proof. And now we choose another vector space, W, which is an R minus 1 dimensional vector space, which is spanned by R vectors, W1 up to WR, whose sum is 0. So in W we have a simplex which contains 0. And now we consider the tensor product of V and W. And in this tensor product, we consider M sets. So the tensor product of V and W, V and U is V and W is something of dimension d plus 1 times r minus 1. And in this tensor product, we consider these sets: AI tensor W1, AI tensor W2, up to AI tensor WR. And we consider it for I equal 1 up to m. So we have exactly the number, although I managed to confuse the indices, we have exactly the number of sets which we can apply Barani's theorem. And of course, 0 is in the convex hull of all these AIs, because 0 is the average of the points in the AIs. So now we can finish the proof. So note that 0 is in the convex hull of each AI, and by Barani's theorem, 0 is the convex combination of 1 point from each of the sets. So 0 is the convex hull of A1 tensor WI1, A2 tensor WI2, and so on up to AM tensor WIM. And now you can see the partition. The partition is according to the indices of these WIs. There were RWIs, W1 up to WR. And now we can split it, and the R parts are given by omega. The J's part will be omega J, all the AKs, so they were tensored with WK. So all the AK, so that IK is J. So this gives us the partition. And if we write 0 as a convex combination of such points, because the only vanishing linear combination of W1 up to WR is the sum being 0, we immediately get that if 0 is some sum of lambda k AK tensor WIK, then, and the coefficient WK are non-negative, then the vectors, when we split this sum into R vectors according to the partition we have just mentioned, then these R vectors are all the same. And also the R coefficients, the R scalars, which correspond to the sum of coefficients, are all the same and equal to 1 over R. So this concludes the proof of Tverberg's theorem. So maybe I rushed a little bit, but I think you can get the impression of the proof. And indeed, it's quite easy. I mean, in a class, you can present it in maybe 40 or 45 minutes. And let me mention that, what? Oh, okay, sorry. And let me mention that very recently, Raudnev found another simple proof, and precisely the same order of difficulty, more or less the same order of difficulty, somewhat more direct. And his idea, which is not so different than other ideas which were used, but he used the right function, is to look directly at a point x and the partition S1 up to SR, so that the sum of the squares of the distances from x to this convex hulls is minimal. And if you choose this function, somehow things simplify. I mean, Tverberg used different function in some of his earlier proofs, but this function really do the job quite easily. Okay, so let me mention now. So this was the proof, and let me mention a problem that it is an interesting problem to find efficient algorithms, either for Barani or for Tverberg's theorem. I mean, the critical point for algorithmic is the proof of Barani's theorem, and it's not known if there is a polynomial algorithm to find points which are guaranteed by Barani's theorem. I mean, yesterday I realized it when I prepared the picture for this talk. So I tried to make the drawing for Tverberg's theorem, and every time I tried, I draw 7 points. I guessed what is the Tverberg partition. It didn't work out. Then I did it again. Again, didn't work out. So this may indicate it's a little difficult. Afterwards, the third time I realized the right way to do it is first to make the partition and then to draw the point. So this is the way eventually it worked. Okay, so this was the first thing. And now I would like to move along to topological generalizations, or topological generalization. And this is unfortunately only a conjecture, and it says the following. Suppose we have a continuous function from the m-dimensional simplex to Rd, where m is this number, d plus 1 times r minus 1. Then there are r pairwise disjoint faces of this simplex, sigma, so whose images have a point in common. Now, if you consider linear functions, then this is just Tverberg's theorem, because the only thing that matters is the images of the points. And this gives you back Tverberg's theorem. But for continuous function, this is still not known. And the case R being a prime number was proved in a seminal paper. Start this direction of, this conjecture exists earlier, but by Barani, Schlossman, and Schutz. And let me tell you a little bit about the idea of the proof. Sorry. Oops. So what is the idea of the proof? Here I will be somewhat more brief than earlier. And the idea I will use not follow the original proof, but somewhat different proof by Sarkaria also. And you do the following. You assume that R is a prime number. You look at two spaces, XR and YR. XR is the R-fold deleted join of this simplex. So I'll tell you in a minute what it is. YR is the R-fold deleted product of RD plus 1. So the deleted product is the product where the diagonal is omitted. The deleted join is some construction on simplicial complexes. It's like a join, except you delete the simplices which are not pairwise disjoint. Again, you don't have to really know precisely what are these definitions, just to get the feeling. And then there is a free action of ZR, the cyclic group of R elements, on both XR and YR. And if there is no point which is simultaneously in the images of R disjoint face, we can obtain an equivariant map, FR, from XR to YR, induced by the original function f. So the original function f induced some equivariant map. The reason this map is defined is the reason we can delete the diagonal is because we assume that the theorem is not true. So we don't need the diagonal. And now we consider this space YR, and we do another operation. We project it into some properly subspace. So we project it by considering all the points, all the R tuples whose sum of coordinate is 0, and then we normalize to get vectors of norm 1, and we get a sphere of dimension a minus 1. So what happens here if you do this, and I mean this is just the idea, but when you do this, you get a map, equivariant map from a space YR, which is highly connected to the sphere, and this is impossible by not so difficult theorem in topology. Actually, when equivariant map, when M is 2, when R is 2, then this is just the Borsuk-Olam theorem. And this is a similar type of results. Now, a further extension was done more recently by Ozaidin and then Volovikov, and again by Sarkaria, to prove this conjecture that I mentioned before about the topological theorem. Well, you use it in several places, both in the free action and also to derive the contradiction from the topological theorem. So use it in several places. And in fact, you can do something for the prime power case. It's much more complicated computation of characteristic classes, and this was done by Ozaidin, Volovikov, and recently Sarkaria. And the general case is still open. It's not clear what to do. It's not even clear that you have to look at ZR action. You can present the problem by some repeated Z2 action. It's not even clear that you have to look at actions at all. You can regard it as some statement about the diagram of faces of a simplex and apply topology directly to there. In any case, nobody knows what to do. So your suggestion is as good as any. So these are topological extensions.
Yes, we believe in the theorem because very similar topological theorems we also conjecture happen
to be false. Yes?
There is connection with cluster report?
Of course, it's very similar to cluster conjecture.
Yeah, it's somewhat similar, but it's not so similar. I mean, yeah. What? Somehow in the later we will mainly deal with the case of 3. So there I don't have to worry so much. So, but if you ask me, I don't know about if I believe it or not. I tend to believe it. Okay, now let me move to another topic, or related of course, and this is the question is, what is the dimension of the Tverberg point? So you look at all the points that belong to the convex hull of R disjoint subsets, R pairwise disjoint subsets of your point for configuration, and you ask what is the dimension. So Tverberg's theorem says that if you have certain amount of points, the dimension is at least 0, so it's not empty. It is reasonable to assume if you have one more point, then the dimension should be 1. If you have 2 more points, the dimension should be 2, and so on. And of course, this is true in the generic case. If the points are sufficiently generic, then the dimension you will get is precisely the extra number of points which you have. Now, it was conjectured that it's enough to assume the points are in general position, and Raudnev proved several special cases, and then again you wanted the dimension of Tverberg point would be at least okay, yes, and but let me now point another direction of studying this dimension of Radon points, and this is, and let me just point to you this 2 configuration in the plane. You see the configuration on the the left-hand side. The configuration on the right-hand side, this is the vertex of the pentagon. The Radon points are one-dimensional. Let's see this. Oh, let me give you the configuration with here the Radon points are one-dimensional. The Radon points actually are this pentagon. And on the other hand, in the configuration in the left-hand side, no matter how you divide them into 2 sets, the intersection of the convex hull is only 0-dimensional. So 5 is one extra point to the number which guarantee Radon partition, but in the left part, the dimension is 0. But there is some compensation for that, and the compensation is that although 5 is smaller than the number which guarantee partition to 3 parts, somehow miraculously you have here a partition to 3 parts where the convex hull have non-empty intersections. Yes, you see. So here the Radon points have 0-dimensional intersection, but very untypically to 5 points in the plane, you can divide them to 3 parts, the red point, the green point, and this point in the middle, and the intersection of the convex hull is non-empty. So is this clear? So this example lead quickly to the following conjecture, which is my conjecture. This is a conjecture which I made 25 years ago, and it says the following. Suppose, and as you can see, the point here is to consider not generic position, but very special point configuration. So suppose you have a set in RD, and we denote as before TR of A, those points in RD which belong to the convex hull of R pairwise disjoint subsets of A. Then if you sum up the dimension of the Tverberg points, of the points which belong to R pairwise disjoint subsets, from 1 to the size of the set, and you have to remember that the dimension of the empty set is counted as -1, then the outcome is always greater or equal to 0. So this captures this phenomena. I mean, if you lose one in the dimension of the radon points, you gain one dimension of the Tverberg point. Now this conjecture already includes Tverberg's theorem, but it's more general. It has, I mean, is it clear, the conjecture? It has somewhat of a, it looks like some statement about CGGs. So I really tried to translate it to also to commutative algebra language to find some sort of free resolution to demonstrate it, and also more than tried, I also tried to ask my commutative algebra friends, but so far there's no understanding of this conjecture in this line. So this is the conjecture, and let me mention that in the plane, this conjecture was proved by Akiva Kadari. So the plane case, I should say that also Tverberg's theorem was proved earlier for the plane by Birch. The planar case is easier because somehow you have ordering of the points somehow. And Akiva Kadari proved around 1980 that the conjecture is true for planar point sets. Okay, now I would like to mention first some refinement of the conjecture and then some specialization to the conjecture, and then try to relate it to some other things. And let, what?
Can you always take the open?
Oh, okay, sorry. I mean, this is what I'm trying to do, but I need to remember. I mean, oh, okay, that's a good algorithm. I mean, okay, so let me briefly mention some refinement of the conjectures. One refinement would say this is only about order types or about oriented matroids. You don't really care. I mean, Tverberg partitions are related to some structure which is not captured by the order type, but maybe the conjecture is still true if you consider an order type and you minimize the Tverberg dimension of all configuration in this order type. So this will be some strengthening. Another strengthening of this conjecture, which seems quite difficult because it includes a topological thing, is instead of talking about dimension, let's talk about homological dimension, the list of non-vanishing homology group, in this function which I mentioned in the topological proof of Tverberg's theorem. Maybe the conjecture is still true in this case. I mean, this is very far-reaching because we don't even know, and there are reason to doubt even the original topological condition. But now let me restrict myself just, what? Oh, sorry. So let me now restrict to what I would like to continue with, and this is about condition for partitions to 3 parts. So now this will be my interest, to find. So of course, if you have 2D plus 3 points, you can always partition them to 3 parts, so the convex hull intersect. And I would like to find condition which will guarantee that partition to 3 parts exists for smaller number of points. In general, this will be complexity-wise a very difficult problem. It's very easy to encode difficult problems, so you don't expect necessary and sufficient condition, but we would like to find condition for partitions to 3 parts when we don't have enough points. And this is a natural problem because if you have points in some Euclidean space, you ask, is there a radon partition? Then this is equivalent to saying that they are affine dependent. This is important geometric invariant, and we would like to find something similar here. And the special cases of my old conjecture would say, if you have d plus 2 plus k points, and the dimension of the radon points, T2 of A, is less than k, then there is non-empty, then there are Tverberg partitions. Then T3 of A is not empty. And for this is not known in general. I don't know when, maybe I knew it 25 years ago, but I think I didn't. At that time, I often eluded myself that I know things. In any case, I was interested in the general conjecture, so I looked very down this special case. But now I'm very interested in this special case, and I cannot prove it. So I don't know. Anyway, so this is the special case, and now I would like to mention the stronger homological version of this conjecture, and let me refer to it as conjecture H, although it's a bit vague. It's not bad. If you have d plus 2 plus k points in the plane, no, not in the plane, in RD, sorry.
Okay.
If you have d plus 2, What? Yeah, no. If you have d plus 2 plus k, yeah. If you have d plus 2 plus k points in Rd, if the homological dimension of the radon points after the map U3, which appeared in the topological proof, is smaller than k, then you have a non-empty partition. Then you have a partition to 3 parts. And this is a conjecture that I would like to put here. And the reason I'm excited about a certain possible applications, I should say that this, since we are dealing here with this reaction, this looks feasible from the algebraic topology point of view. So, it's not feasible to me. I try to work with several people. I mean, most advanced ideas were offered by Eric Babson that we thought about this. So far, it looks there is much to be done. It may be feasible, may be plausible, but we don't know how to do it. But this looks feasible, at least. Anyway, so where are we? Okay. So now I would like to draw attention to special class of configuration of points. And this is configuration of points which come from graphs. So if you have a graph, or eventually consider also planar graphs, then you can consider just the incidence vectors of the edges. So you consider you have a graph with set of vertices V and set of edges E, and you consider the configuration of points which are the incidence vectors of edges of the graphs. And now a general problem which I think is of interest is what can be said about affine dependencies, the radon points, maybe Tverberg points of such point configurations. This is similar to problems which we are considering in graph theory. It's somewhat, if you take the signed incident vectors, it's very closely related to flows. Somehow I didn't see this treated in graph theory. Let me just explain to you what are the configuration which correspond to a graph. Here is a graph. It has 4 vertices, 1, 2, 3, 4, and 4 edges. And these are the incidence vectors. So 1, 1, 0, 0, 0, 1, 1, 0, and so on. So is it clear how to associate configuration of points from a graph? Okay, now, the reason to be interested in Tverberg partition for graphs is that the partition gives you, in a natural way, a coloring. And as we see, there is much interest in question related to coloring of graph. So I will repeat some of what Noga has said, and I'll remind you of the 4-color theorem, which says that every planar map is 4-colorable. And as Noga indicated, this is equivalent to say that every cubic, let's say 2 connected, planar graph is 3-edge colorable. So whenever we have a cubic planar 3-connected graph, we can color the edges with 3 colors. So again, the Appel-Haken proof, and here I forgot one of the authors, use the computers. It's a great scientific mark point, the heavy use of computers in proofs. All this was discussed. And finding human conceptual proof is on the back of the mind of many mathematicians. So I can mention that Dror Bar-Natan offered some Lie algebra formulation. He's a colleague of mine. In the most recent conference I attended, I learned about some approach using toric varieties. And in this I didn't know when I prepared the slide. In the previous talk, Noga mentioned an approach using some polynomials and their coefficients. And now, let me jump to the possible relation between Tverberg points and the 4-color theorem. And note that when you have a 3-coloring for the edges of a cubic graph, then this is equivalent, I should say connected cubic graph. This is equivalent to the existence of Tverberg partition to the configuration of points which correspond to the graph. Now, I should mention that this is planar cubic graphs are very rare objects. This is related to the problem that Misha referred to in his talk. the only exponential number of planar cubic graphs. The number of cubic graphs in general is something like n factorial or behavior like this. So they are very rare objects. And we would like to find some reason why this rare class of graphs are 3-edge colorable. And here is a possible direction. What we really want to show is that there is a Tverberg partition into 3 parts. But this configuration of points, there are not enough points to guarantee a Tverberg partition. So you need some special condition that imply that a Tverberg partition to 3 parts exists. And the condition that might work is this homological condition, which corresponds to the dimension or the homological dimension of the radon points. So although 3 coloring are combinatorial objects which are unfeasible, I mean, it's very difficult to 3 color, the radon points correspond to combinatorial things which are in the area which we can handle. It's linear algebra, and there may be some ways to treat them. So my conjecture that I suggest to you here, so suppose you have a configuration of points correspond to a cubic planar graph, and this is 3n/2 points in an n-1 dimensional space, unless the graph is bipartite, forget about this case. Then what we expect is that the dimension of the radon points is n/2. Or similar dimension, the homological dimension in this conjecture is n/2. And the conjecture is that the homological dimension is by 1 less. So this is, as I said, that these 2 conjectures would imply the 4-color theorem. I have more confidence about this. I don't know why, but this at least relates to things I thought about for a long time without success. This gives you some strange sense of confidence, or probably unjustified. As for the conjecture which corresponds to the topological properties of radon points of plane graphs, it's at present only a wishful thinking. It's not so easy to check it. Although, again, as I said, because we are dealing here with radon points, with affine dependency, these are combinatorial objects which are feasible. I mean, at least.
Conjecture P is a specialization of H.
No. Conjecture.
Both of those are needed?
Both of those. This is topological conjecture which guarantee partition to 3 parts. And this is something about planar maps, that some topology of some radon points is not as general as you would expect. And together, they would imply the 4-color theorem. So there is still some work to be done. In any case, at present, this conjecture is wishful thinking. So it may be tractable. I mean, it may be tractable and easily be seen to be false, but even if it is true, it may be tractable. OK, so let me now, unless there are some questions, or some people see the proofs right away. What? Sorry, what?
There is planarity coming in.
I mean, this is a configuration corresponding to a cubic planar graph. I mean, you can, so this, of course, this is not true for the Peterson graph. We know it. I mean, if this conjecture is true, right? But this is not true for the. I can bet it's not true for the Peterson graph. But for planar graph, I would expect this is. This is too strong. But I suggest. Well, I will try to look at it. But
What does the word conjecture mean?
what?
What does the word conjecture mean?
Well, I mean, in general, you ask, or?
For instance, in this case, does it mean anything? You wrote wishful thinking.
Okay, so you can take it as the definition of conjecture in this particular case. I mean, you know. Okay, so this is what I have. What?
Because maybe it's easy.
Don can explain this idea of Don what means the word conjecture. Well, that's not right.
Well, I mean, it's. I don't know if this leave up to Misha's definition of conjecture, but maybe we need a different word for ad hoc conjectures or tentative conjecture. I mean,
Whether you hope it is true or you're convinced it is true.
no. So as I said, wishful thinking. I hope it is true, or something like this.
Code H and code P.
What? Okay, so let me, to conclude my lecture, come back to some more solid grounds of other applications of Tverberg's theorem. I should say this subject deserves an entire lecture, and it's a little injustice just to mention it at the end, but there is a very nice, beautiful combinatorial problem about the number of halving lines in the plane, and more generally having hyperplanes for configuration of endpoints. How many such, you have endpoints in the plane, in how many ways you can split them to two parts by a line. The planar case is closely related to a nice problem in algebra. You look at the symmetric group, and you look at reduced world in adjacent transpositions, and you ask what is the maximum number given generating can appear. And improving on earlier bounds by Lovas, recently there are some bounds on this problem. And there are very nice extension of Tverberg's theorem, which are used to prove some non-trivial results in the high-dimensional case. Unfortunately, I don't have the time to explain how it goes, but if I can lead you to the reference if you're interested. So let me, what? Oh, yeah, sure. And let me finish by mentioning two other problems. Now, Eckhoff, which really follow Gromov's guidelines about using the word conjecture.
Don't mind.
What?
Don Zagier suggested that when I was giving my discussion, I referred to him, yeah?
Ah, okay. So
Don't take credit for that.
maybe joint, I mean.
No, you just ask him to join, Don explained this to me, and I just repeated.
But you endorse it also?
Yes, absolutely.
Oh, okay. So, yeah, so if we're talking about guidelines, we can also refer to you because, you know, it's... So, Eckhoff asked many years ago if the Tverberg theorem follows purely combinatorially from Radon's theorem. So, is it true that for any closure operator, for any abstract closure operator, if you define Tverberg number and Radon number, you have this relation? So just by words, it says, does Tverberg's theorem follows purely combinatorially from Radon's theorem? And for years, he struggled with anybody who tried to call it Eckhoff conjecture. He said, I didn't think about it enough to call it a conjecture. It may be false. So I think after 30 years, he is ready to conjecture it. So he called it the partition conjecture. So
That's right.
what?
That's right. 20 years is a conjecture.
Yeah, but I don't know. I still like, I mean, my attitude. So this is a conjecture. I mean, I try to prove it. And finally, Sirksma, another mathematician who studied this, asked what is, if you have the right number to guarantee one Tverberg partition, what is the minimal number? And there is, if you look at the points of the simplex with repeated appropriately, you get that there are r minus 1 factorial to the power d distinct partitions, and he conjectured, again, I don't know how deep, I mean, he moved to being a labor union leader, and then you know, if somebody don't like your conjecture, you break his leg or something. So in any case, he conjectured that this is the number you always need, r minus 1 factorial to the power d. Okay, this is it. I have 3 copies of slides if you want.